folks, so far we've been able to solve problems with right-angled triangles by using the primary trig ratios. So what we want to do now is see if we can extend some of these ideas to include triangles that are not right-angled. So I'm just going to draw any old triangle, and we're going to assume that it's not right-angled, okay, and see what we can do about finding relationships between the sides and angles of this triangle. So the first thing I'm going to do is I'm going to label this triangle A, B, C, okay, and I'm going to let these capital letters represent the angles in the triangle. So angle A, angle B, and angle C. And the way I'm going to represent the side lengths is the opposite side to A is going to be called lowercase a, the opposite side to B is going to be called lowercase b, and the opposite side to C will be lowercase c. Okay? Now, when we come up to something new, it would be really nice if we can recycle some old ideas. So we're going to do something that we've seen in some of the application problems from the past unit. So I'm going to start at this vertex C, and I'm going to draw the height of the triangle, which is perpendicular, in this case here, to side C. And what I've done is I've created two right-angled triangles. So let's see if we can work with primary trig ratios on these individual triangles and then bring them together some way to find the relationships that only includes the sides and angles of the big triangle. So I'll start by calling this side H here. And let's look at the right side. Let's look at the left side first. Okay, so I've got the opposite side to angle A, which is H, and I have the hypotenuse of this right angle triangle, which happens to be side B from the larger triangle. So opposite hypotenuse, let's use the sine ratio. So sine of angle A is equal to H over B. Now let's take a look at the right hand side, and I see something similar because the height here is just the opposite side to angle B, and the hypotenuse happens to be side A, which is in the larger triangle. So let's write out again sine of angle B is equal to H over side A. Okay? Now we have this system of equations. Now remember, the relationship I'm looking for should only include the side lengths of the original triangle and the angles of the original triangle. So what I'd like to do is find a way to get rid of that H variable. And I think you can probably see how we're going to do that. We'll do that by solving for H here. So H is equal to, bring that over, B sine A. And then here we have H is equal to A sine B. And since these two H variables are the same, I know if those are equal, these two expressions must be equal. And so we have B sine A equals A sine B. And what we have here is a relationship between two of the sides and two of the angles in this triangle. Okay? Now before we take a look at how we can apply this, we're going to change this up a little here. This is not too hard to remember, but what we're going to do is you're going to bring everything in terms of A to one side of the equation. So I'll take this in version 1 of our property. We're going to take side A to the left side by dividing, so we're going to end up with sine A over A, and then we're going to take side B to the right side and write the relationship in this way. Okay. Now let's go back to the triangle here. I just happen to label A, B, and C, but I could have changed these around any way I liked. So let's say this had become side angle C, and that had become side C, and I had followed the exact same pattern. I would have found that that was also equal to sine A over A. So the way in which we usually write this property, okay, just to demonstrate that it would work for any ratio of sine of an angle and its opposite side, we write the property in this way. Now, I said there's two versions because what I could have done is I could have, instead of dividing the side lengths to each side, is to divide the sine of the angles to each side. So another way in which we write this property is A over sine A equals B over sine B equals C over sine C. Okay. And you can choose to work with one of these all the time, or you might say, well, when my variable, when my unknown is an angle, I might as well work with this version so that my variable will be in the numerator. However, if my unknown is a side length, I might as well work with this version so that my variable will automatically be in the numerator. Okay, so you can choose to just use either one and then do the appropriate algebra, or choose the one that will put your variable in the numerator. Okay, so let's see how we can actually use this in application form. So let's say I have this triangle here. So let's say that's 8 and that's 7, and I know that this is an angle of 35 degrees. Okay. Well, let's see what I could determine, if I can determine anything here. Well, let's take a look at this equation here. Okay, I know angle 35 degrees and its opposite side of 7, so I could fill out the left side of this equation, and I know side length 8. I could determine its opposite angle. Okay, so let's take this version of the equation. One thing you'll notice, and if you need to do it at the beginning, certainly go ahead and do it, but I'm going to try to encourage you to get out of the habit of labeling the triangle A, B, and C. I want you to think of what this relationship says. It says the ratio of the sine of an angle to an opposite side is equal to the sine of any other angle to its opposite side. Okay, so let's write this out. So here we've got, let's say we're looking for theta, so I've got sine theta. Okay, and what do I need in the denominator? Its opposite side, so 8. Okay, by the way, we'll call this example 1. And on the other side of the equation, well, I know angle 35, so sine of 35 degrees over its opposite side 7, and I have an equation with only one variable. Okay, so in order to solve that, sine theta is equal to 8 sine 35 degrees over 7, and then theta is just inverse sine of 8 times sine 35 degrees over 7. Okay, and you can go ahead and solve that. I don't actually happen to have a calculator nearby, so you can solve that yourselves. Okay, but what we've managed to do is solve for another component of this triangle, even though it was not a right angle triangle. Okay, now let's think about it. Once you have that angle, you can then use the fact that the sum is equal to 180 to find the third angle, and then you could apply the sine law again. Okay, now that you have this angle, to find the missing side. So we see that with the sine law, we can solve this triangle, find everything that's missing about it. So let's take a look at another example here, and let's maybe take one where we're looking for side length. Okay, so example 2. Okay, so let's say we have this triangle here. Okay, so let's say this is 10, okay, and let's say this is 30, and let's say this is, I don't know, what does this look like, 80, okay, and let's say I'm looking for this side length here. Okay, so let's take a look at what we have. Okay, so I'm looking for this side length here, so I'm going to work with this version of the equation, and I have x over, wait a minute, I don't have its opposite angle. But in this case here, that's not a problem, because I know the other two angles in the triangle, so sometimes you do have to do a little bit of work. So let's find this out. So 80 plus 30 is 110, so this angle here would be 70. So x over sine 70 degrees is equal to, and now we have this side, which is 10, divided by the sine of its opposite angle, 30 degrees. And so x can be found by just multiplying this to the other side, 10 times sine 70 over sine 30. And you can calculate that on your own. Okay, so another example, here we had different information. We had two angles and a side. Here we had two sides and an angle, and we were able to solve for the other components of the triangle. Okay, let's look at one more example here. Let's look at example 3. Okay, so let's say we have this triangle here.
So let's say I know that this is an angle of 80 degrees, and I know that this, say, side length is 5, okay, and this side length here is 8, and I want to look for this side length here. Okay, so let's set up the sine law. Okay, so I'm looking for this side, so I'll put that one in the numerator. So that would be divided by the sine of its angle, sine 80 degrees, is equal to